Bismillahirrahmanirrahim. Welcome to the channel. My name is Asim Amjad. In this video lecture, we start lecture number 13, that is design of beams. In this video lecture, we are going to design for an appropriate beam to be used in real world engineering problem. Let's say that we have some loading and we want to design for the beam. So we have a steel beam that is subjected to the loading below and want to design for an appropriate wide flange I-beam to carry that load. So at the first step of this design, we need to know what the shear force and bending moment diagrams are going to be that. So we are going to design against. So let's begin by drawing those shear force and bending moment diagrams. So here are the results. Make sure you can do this. If you don't remember how to do the shear force and bending moment diagram, you can refer back to my lecture number 9. Okay, from shear stress and bending moment diagram, we know the maximum shear force is 175.5 kilonewton and the maximum bending moment is 130.5 kilonewton meter. Okay, now let's identify types of stresses that is acting on different parts of the cross section, and this beam now is going to be subjected to elastic flexure stresses and also the transfer shear stresses that is shown here. And so we are going to look at three different points in the cross section as we go to design and look for the critical point. And the points are shown here, that is A, B and C. So at point A, the top is where we will say, or it could be at the bottom as well, where the maximum flexure stresses occur. And so that because this is our formula for the maximum flexure stresses, we see that the distance C for this from the neutral axis give us the largest flexure stresses. So if I draw a stress plot, we see that there is no shear force at the outer surface, and so the maximum flexure stress can be calculated at that point. At point B now, when we put a small differential slice of our beam, we saw that we got both flexure stresses and the shear stresses, and so we will look at that point as being an area where we have a combination of stresses that may be critical. One point that I want to make is slice. I'm looking at the cut below the neutral axis. Down here or above the neutral axis, the shear stress direction changes. And finally at point C, because that's the neutral axis and that's the point where the maximum transfer shear stress will occur, and so that's another critical point we want to look at in our design. At the neutral axis, we know that the flexure stress is actually equals to 0. So by looking at these three critical points, we will come up with the best design to achieve our desired result anywhere along the beam. Okay, we are going to review now what called the maximum normal stress failure theory, and we have discussed this theory before, and we say that the failure occurs when the sigma actual is greater than the sigma experience. The normal stress experience is greater than whether normal stress we just define as being the failure stress. So we have a situation where we have a pure beam bending, and we said that the section modulus was the I over the distance to the stream fiber, that is C, and so the sigma max is equal to moment experience over the section modulus. And so for design, we want the section modulus of our actual beam to be greater than or equal to the maximum moment that's going to be experienced in our beam over what we are going to determine is being our actual or allowed stress, and again maximum bending moment expected here. So as an engineer, we insert in our design a factor of safety, and we want that factor of safety to be greater than 1, and we as the engineer define what we are going to use this failure. Most of the time it's the yield stress over the actual stress that experience, and so we have the sigma failure over the actual or allowed stress, actual stress that's experienced. So now we have sigma failure over the actual or allowed stress that we are going to design for. We take that actual allowed stress and substitute it here, and we know that the maximum bending moment, or we can determine what the maximum bending moment is expected from our shear force and bending moment diagram, and we can design or find a cross section that has a section modulus that's large enough to accept the load. And so this section modulus, as I had mentioned earlier, can be found at a number of sources, and they are listed in tables in the manual of steel construction. And so as a conclusion, for the maximum normal stress theory, failure occurs when the sigma experience is greater than the sigma failure. By experience, we generally use this theory of failure and design for brittle materials. So it's not good for the ductile material like steel, aluminum, plastic, as they have a tendency to fail and shear, but for brittle material this is a good failure theory to use. Now we look the maximum shear stress failure theory, also known as Teresa yield criterion. And so far the maximum shear stress theory, we know that failure occurs when our shear stress experience is greater than our failure shear stress. And so recall, we have a design and we built in a factor of safety, and the factor of safety is defined as the failure stress over the actual stress. Now instead of working with normal stress, we are going to be working with shear stress, and so we want to factor of safety that's greater than 1 to avoid the failure. Factor of safety is the design criteria for different type of engineering component or structures, and the designer defines what the failure is going to be or designs against what the failure mode is going to be. And for the normal stress theory, we use the simple tension test to look at the failure to design our stress strain diagram. And what we are going to assume that even in complex loading condition, when we have non-uniform bending and we see that we have flexure and shear, and we are going to say that the material has the same capability as we found in the simple tension test. So here is our simple tension test, and here are our failure, and we pull on it with uniaxial load, but now we will draw a Mohr circle, and we can see from different planes at the stress plot the different orientation we can also experience the shear stress. And so if we go out and draw our Mohr circle on the horizontal plane, we have our failure normal stress, and on the other plane we have zero stress. And so we have now draw more circles and we see that there's an orientation for our stress block where we are going to have maximum shear stress, and that's where we are concerned about in the maximum shear stress theory. So tau failure, let's say that our sigma failure is the yield proportional limit, and the failure is defined as the yielding or reaching the proportional limit of our material. And so for tau failure, that's also going to be the yield or proportional limit, and so that's going to be our Mohr circle, one half of the sigma yield. And so far factor of safety is the failure stress over actual stress, and we are saying that our failure stress is defined as the proportional limit or yield stress or the shear stress that's going to be over our actual stress, and a factor of safety greater than 1 is going to go ahead and avoid failure. So this theory is particularly good for the ductile material and light steel, aluminum, plastic, and that's because yield in ductile material is usually caused by a slippage of the crystal planes along the maximum shear stress surface. And so now we have talked about two different failure theories that we can use in design, and we will go back and decide how are we going to proceed with our design of engineering beam or engineering structure. Okay, so here is our model and the loading, and as we said we are going to check these three critical points A, B and C on the cross section. So the first area we are going to check is the top of the stream fiber of the cross section and the one that furthest from the neutral axis, which it be at the top or the bottom, and that's where we see our maximum flexure stresses are occur. And then we are going to check somewhere in between the outer surface and the neutral surface, that is the point B, where we get a combination of flexure stress and the shear stress. And at last we check at point C, which is at the neutral axis, where we see the maximum transfer stresses. So to design the beam we are actually going to assume that the stream fibers, the cross section at point A is going to be critical, and that's how we are going to select our beam cross section. And then we are going to go back through and check to make sure that also achieves, and it's good for point B and C as well. So we will check all the three locations. So far our problem, let's begin by deciding what kind of failure theories we are going to use. And as you know, we have talked about a couple of different failure theories. For this problem, we are going to use the maximum shear stress theory because this is a steel beam, and this theory is good for the ductile materials, whereas the maximum normal stress theory is good for the brittle material. And so far, this theory failure occurs when the shear stress is greater than the shear stress that is defined for the failure. And so we draw our Mohr circle that is shown here from this simple tension test, and we found that the tau max was equal to the sigma max over 2. And so far at point A we have got our sigma max is our maximum flexure stress. So tau max is going to be the maximum flexure stress divided by 2, and it is shown here. And so we can also show in term of the section modulus. So we have the tau max is equal to the maximum moment experience divided by 2, times the section modulus, that is the h, and we know that h is equal to I over c. So place this c into the denominator, then I over c would become h. And for design, we want that the section modulus that we pick, or the beam that we pick, or the particular cross section to be greater than or equal to the largest moment we experience divided by 2 times the allowable shear stress that we will be able to accept, that is shown here. And so remember, factor of safety is failure stress over the actual stress. And in this case, we are going to say that the failure stress is the shear stress, or we are going to say that the yield is equal to the proportional limit. So that the same as the yield normal stress divided by 2 over the normal stress actual divided by 2. And we can factor out these two, and we find out that here is our result. So we will go ahead and substitute in tau actual or allowed as being sigma actual allowed over 2. So from here you see h section modulus is greater than or equal to moment max over 2 times tau actual allowed, and tau actual allowed is calculated as here, that is sigma or normal stress actual load over 2. So substitute this term here, and these two is cancel out, then section modulus h is greater than or equal to moment max at maximum over sigma normal stress actual allowed. And so now we want to design our section modulus list so that it's greater than or equal to the maximum moment of the experience divided by this value, that is come up with the allowed normal stress over here. So let's go back to our shear force and bending moment diagram, and the maximum moment that we experience is 130.5 kilonewton meter. So we are going to use sigma proportion limit or yield from a reference to be 250 megapascal, and for our steel that we are using, we will go ahead and use a factor of safety of 1.2 for the bridge beam design. And I do the conversion factor, and I find that I need a section modulus for my wide flange I beam that's going to carry the load to be greater than or equal to 626.4 times 10 to the third millimeter cube. Now you have to find from the table wide flange I beam and try to select the I beam that has the section modulus is greater than this number, and so I have selected W 356 times 45, and its section modulus is H is equal to 688 times 10 third cubic millimeter, which is definitely greater than the words required or words needed. And again you can find these values in the standard reference online. And so that the beam we are going to choose and we will design against that, we will make sure now we have designed it based on the maximum flexural stresses at the outer fiber. We will now check to make sure it will work at point B, where we have a combination of flexural stress and the shear stress, and at point C at the neutral axis where we experience the maximum shear stress. We said that we were going to select this wide flange I beam to carry the load, and now we have to do our checks. So this is the beam cross section that we have selected. I have drawn a diagram of that cross section from the reference. I wrote the values for the depth and the width and etc. So because of symmetricity, the neutral axis lies in the center. And so far the critical checks, we are going to check the maximum flexure stress at the stream fiber, and that's going to be the same at the top or the bottom. That's the point A. And then we have to do a combination of flexure stress and shear force. Generally on the I beam we pick the junction between the flange and the web, and we also pick the point C, which is at its neutral axis for the maximum transfer shear stress we experience by the cross section. And so three checks: maximum flexure stress, maximum shear stress at the neutral axis, and a combination which we pick to be at the junction of the web and the flange. So, and due to the highest combination of the bending moment and the shear force along the length of the beam, and so the junction of the web and the flange, the simultaneously high normal stress to the bending and the large transfer shear stress made it a good critical point for investigation. So for critical check at A, we have designed the beam based on the maximum flexure stress on it. Better meet those specifications, but let's go ahead and go through the procedure anyway to double check it. We said that our allowed normal stress we going to be the yield normal stress divided by the factor of safety, which was now 208.3 megapascal, but we are designing based on the shear stress since we are using this simple tension test as being inductive of more complex loading. So we already defined these term in above. The proportion limit is 250 megapascal and the factor of safety is also given, that is 1.2, and we know that the sigma actual allow is equal to the 208.3 megapascal. So we know that the actual load where the actual shear stress is going to be that normal stress load divided by 2, or in this case 104.6 megapascal. Okay, and so here the maximum flexure stress formula, and we know that I is for my cross section from a reference from the Y flange I beam, and so I can go ahead and substitute in, and I find that the normal stress is, and by doing some conversion factors I find the maximum normal stress is 189.8 megapascal, and again this is based on our maximum moment experience of 130.5 kilonewton, and tau A is equal to the sigma or the normal stress at A will be the sigma A divided by 2 or 94.9 megapascal, and then A that's experience at outer fiber is less than, which is 104.6 megapascal, and so in fact our I beam is going to be able to withstand with in our design constraint the stresses that are experienced at the outer fiber or at point A, and so we are okay there, and we will continue on by checking the junction at the flange in the web and the neutral axis, and if they all work we will good to go. Now we are going to check the transfer shear stress experience at the neutral axis where maximum transfer shear stress is occurred at point C. So for the maximum transfer shear stress, this formula is at point C. We developed it earlier. So we need the Vmax, the maximum shear force experience along the length of the beam, and go back to the shear force bending moment diagram. The maximum shear force experience along the length of beam is equal to 175.5 kilonewton. And so now we have the Vmax, and we know what I is for the cross section, and at point C we know that the width is 6.9 millimeter, and so we still need the Q or our first moment of outer area, and so Q is the first moment of outer area. In this case we are going to break down the outer area from the neutral surface or the neutral axis in two standard shape. The first one is the web portion here, and so the y bar to its neutral axis is 166 divided by 2 times its area, which is 6.9 times 166.2 millimeter. And then I have to use the other standard shape, which is the flange, and y bar is 166.2 plus 9.8 over 2, then multiply that by the area of the flange, which is 171 millimeter times 9.8 millimeter, and that's equal to QC, that is 3 lakh 82,000 cubic millimeter. Now we substitute all these values in this equation, and then we calculate the shear stress experience, that is 80.3 megapascal. So if you recall back, the allowable shear stress which we found was the 104.6 megapascal, and so again we are okay with this beam being selected for the critical check at the neutral axis or point C. Okay, now we are going to finish up the design of the beam to be used in this real world engineering problem, and we have done some critical checks, and we also looked at the maximum flexure stress at the outer fiber, and we have looked at the maximum transfer shear stress experience at the neutral axis at point C. So now we are going to check the last point, which is the at point B, where we have a combination of normal stresses or the shear stresses. And we said that the junction of the web and the flange simultaneously high normal stress due to the bending and large flexure stress made it a critical point for investigation. So we are looking at point B. So the question becomes, since it's a combination of normal stress and the shear stress, where along the beam does the highest combination of bending moment and the shear force occur, and what are those values? So now go back to the shear force and bending moment diagram and find the largest combination of shear force and the bending moment, and that is the 175.5 kilonewton for maximum shear force, and the bending moment at this point is 105.3 kilonewton meter. Okay, so now we have those values, and we can now solve for the shear stress experience at point B using our shear stress transfer shear stress formula. And so what we need to do is we need to first find the moment of outward area at point B. So I made a cut at point B, and y bar is out to this area is 166.2 plus 9.8 millimeter divided by 2. This value gives the value of y bar, and this value is measured from this point to the center of this rectangle of this section, times the area of the outward area, which is 171 millimeter times the 9.8 millimeter, and the QC would become 286,730 cubic millimeter. This is comma. And so I have the V max, and I have the first moment of outer area, that is Q, and I got my I, and I also know what my B is. So at point B we can solve for the transfer shear stress, and it's end up with 60.3 megapascal. Now we also have to find at point B the fracture stress so that the normal stress, and so to determine that we take the moment value at the cross section, that is 105.3 kilonewton meter. This value is come from the shear force and bending moment diagram, and y is the distance on the cross section from the neutral axis, that is shown here 166.2 millimeter. I have my conversion factor, and over I, that is 121 times 10 raised to power 6 millimeter 4. This value is come from the reference, and the sigma B would be 144.6 megapascal. And now I can draw my stress plot, which has got a combination of the normal and the shear stress as shown. So we have our shear stress at point B, our normal stress at point B, and what we can do now is we can draw a Mohr circle. Now we find the maximum shear stress experience because that's what we are designing against. And so here my Mohr circle I can find in the center, that is 72.3 comma 0, and I can find the radius, and therefore from the radius I know that my maximum shear stress at point B is 94.1 megapascals, and that is less than the allowable shear stress that we are designing for, which was 104.6 megapascals. And so again we are okay, and we have now checked A, B and C critical points, and all of them are good enough for our design. And so we have now arrived at our final answer. And so we are going to select the 356 time 45 wide flange I beam with the section modulus, and it will work to carry the load that desired. And so you now have a very nice procedure for designing a real world engineering beam. And so that's where we will finish this lecture. Thank you.